Okay, today we'll continue with the same topic, same chapter, fluids in motion. Last time I talked you the expression for pressure difference, velocity of efflux, and P is equal to H rho G. How can we find using Bernoulli's theorem? Today we will learn about the viscosity. Our topic is viscosity. Viscosity. Viscosity, what is viscosity? We say it is the property of a liquid. It is the property of a liquid not to flow or to oppose its own motion. Not to flow, or to oppose its own flow. Viscosity. In other words, we can take it this way. Viscosity is a kind of liquid friction. Every liquid has tendency not to flow. Because if any liquid you make it flow, then after some time it stops. Or you can see the water coming in from the tap. The water drop slowly when the tap is closed. You see that water drop will come out in a little quantity and slowly it stops. When the tendency of a liquid to oppose its own motion or to oppose its own flow or to oppose the motion is called viscosity. It was again given by Newton. He said when the liquid flows, the liquid is made up of different layers. Liquid layers are there, surface is there. One surface comes in contact with the other surface. Between the two surfaces, there will be relative motion. Relative motion, that means there will be opposition there. So that opposition causes the liquid not to flow. And he said that there will be a force acting between them. That force is known as viscous force, or between the two different layers of the liquid, viscous force or the viscous drag. That is denoted by F. And he said that F is proportional to the area of the surface, imaginary surface created by the flow of liquid or fluid. And this F is that is viscous force, or we call it viscous drag. F is proportional to dV by dx. dV by dx is called velocity gradient. Velocity gradient. Velocity gradient is dV by dx. That means the rate of velocity with respect to the width of the liquid, width of the surface, width of the one surface and the width. If we combine the two proportionality, we get like this: A dV by dx. We have F, this sign we change with the sign beta, that is A dV by dx. And we put a minus sign here. Minus sign is to oppose the flow. Then this constant over there is minus eta, where eta is constant and is known as coefficient of viscosity. Coefficient of viscosity. Viscosity. You know, some fluid will be more viscous. They will have more tendency not to flow. Normally, the sticky kind of liquid, they will have higher value of viscosity. And the little non-sticky type of liquid will have less value of viscosity, but every liquid or every fluid will have viscosity. So this is F is the viscous force. Viscous force formula is this much, and minus sign is there to oppose the motion. We find the unit of viscosity. Unit of viscosity. From this equation we can calculate the unit of viscosity. What can be the unit? F by A. If you check. If you make beta the subject, the answer will come as F by A into dx by dV. F by A is pressure, with that we can write Pascal or Newton per meter square. Dx means dx means meter and dV means meter per second. So meter per second comes up Pascal seconds. The SI unit of eta is PAS, that is Pascal second, or this thing is also known as PL, we call it PL. PL is Poisson. PL full form is Poisson. Poissle. double yielding cohesive. In short, we can say Pascal second. That is the SI unit of the coefficient of viscosity. Now we can find the dimension also of eta. Dimension of eta. Pascal means pressure, force by area. What is the dimension of force? We know mLT minus 2. Area is L square into second. Second is 10. Let us arrange it. The answer will come ml minus 1 t minus 1. This is the dimension of coefficient of viscosity, that is denoted by a symbol like this eta. This symbol in class 10, I think you had used it as efficiency of a machine, efficiency eta, the same symbol. But here in the chapter fluids in motion, this eta is known as coefficient of viscosity. Every liquid has a different value of viscosity. Now, how to define coefficient of viscosity? This is the constant. How to give definition of it? The definition comes from this equation. Definition we give using this equation. If we say, if I take area value unit, that is unit area, and dV by dx means velocity gradient also value 1 unit, then F will be equal to eta. That is coefficient of viscosity is the viscous force between the liquid layers of unit area and unit potential gradient. We can say that this coefficient of viscosity is defined as the viscous force acting between the liquid layers of unit area and unit velocity gradient. Now this is coefficient of viscosity, and because of coefficient of viscosity there will be viscous force acting against the motion. Okay. Now we have the formula to be derived as per the reduced flavor is this one. Stokes formula. There is a formula called Stokes formula. Stokes formula for viscous force on a spherical body in a medium. The medium can be fluid, can be gas, can be a liquid medium. Okay. To derive the formula, we assume let F viscous force, F is the viscous force, is proportional to the viscosity of the medium eta, and it depends upon the radius of the spherical body, radius size that means, and it depends upon the velocity of the body. Three factors we assume, and we will be raising the power ourselves, anything like x, y, z, and raise the power. And the method of dimension I am using to find the formula. So that F, this thing will replace by a constant k, eta x, r to the power y, v to the power z. We will make the dimension of both the sides equal. Force dimension is mLT minus 2. K is a constant, no dimension. Eta dimension just now we formed. ml minus 1, t minus 1, power x. R is radius, that is length. Y. V is velocity, LT minus 1, power z. Okay, now we have the method of dimension to calculate the value of x, y, z. These factors we have to know ourselves. Okay, these are the factors on which the viscous force made, viscosity force or viscous drag may depend on these factors. Or here I put together M power is coming x, L power is coming at minus x plus y plus z, power of t is coming at minus x minus z. Now that equating powers. Equating powers. When we equate power, x value become 1, x value is 1. 1 is equal to this, that is minus x plus y plus z is equal to 1, and this one minus 2 is equal to minus x minus z. Okay, we have the value of x1, let us put the value here, minus 2, minus x value is 1, minus z will come this side plus z, minus 1 plus 2, therefore z value is coming 1. Now we have x and z both known, let us put that value here, minus x value is 1, y value is going to calculate, z value is also 1, is equal to 1, this will cut, y value also will come 1. Then this x, y, z, all the three of them have the value equal to 1. Let us put it back there. Therefore, we write like this, therefore, f is equal to k eta r v, power is 1 and like Stokes found k value equal to pi by k value equal to 6 pi by experiment. About this experiment you don't have to know, you just have to know that Stokes found the value of constant k equal to 6 pi. They put the value back on here. Therefore f is equal to, it becomes 6 pi eta r v. This is the formula. And this formula is applicable for a spherical body when the spherical body moves in a medium. When it moves in a viscous medium. Viscous medium can be air, can be liquid, or can be any other gases. So the viscous force will be acting in what direction? In the direction opposite to the motion. Suppose drop is falling down, then the viscous force will act up. If the drop is moving up, it may happen because if the density of the drop is less than the density of the medium, the drop will be rising up. In that case, viscous force will be acting in the downward direction. And this formula is known as Stokes formula. This formula is known as Stokes formula. Okay. This derivation we have in syllabus, very well, so we will do this. Now, keep heading. Expression for terminal velocity. Expression for terminal velocity of a spherical body. In a medium. Of course, the medium is viscous medium. In the viscous medium, what is terminal velocity and how do we find this expression? Okay. What happens? Suppose when a spherical body falls in a medium, such that it falls down with a constant velocity. That constant velocity is known as terminal velocity. That means the body will be in dynamic equilibrium. Say for example, raindrops when reaches near the earth's surface, it falls down with the same velocity all the time, Raindrops are spherical in shape. So the velocity, the steady or the constant velocity with which the raindrops fall down is known as terminal velocity. And we are going to find a formula for it. Okay, how to find formula? Suppose we have a spherical drop like this, which is falling down in a medium. So medium can be air, can be some other medium. This can be liquid medium or can be any gas medium over here. And if it is the raindrops, it should be air then in that case. Okay, let us see what are the forces acting here. And what is the condition under which the drop can fall down with a constant velocity. Weight of the drop W is mg is acting downward. Then viscous force must be acting upward. Then the viscous force F. And F value is almost 6 pi eta r v. Just now we found the right. Okay, now this medium will give upthrust also. Upthrust will act in upward direction. Because any fluid where a body is moving in a fluid, the body experiences an upward force called upthrust. Archimedes principle, I think you know. So upthrust is also acting upward. And what is the formula of upthrust? The upthrust formula we have V dg. D means the density of the medium and at rho and g. This is the formula of upthrust. V rho g. The medium which gives upthrust. The medium is this medium. The density of this medium I take rho. And the density of the drop I take d. Density of the drop, the object, a spherical object is d. Okay. So the drop is still moving down. So which force is supposed to be bigger? W is supposed to be bigger than these two. So we write an equation of motion like this. W minus U plus F equal to mass into acceleration. Mass of the drop is the actual ma. Writing W minus U minus F equal to 0, because what type of velocity this drop is falling with? Constant velocity. That velocity is only called terminal velocity. So acceleration is 0. When this V we can write as Vt, this is terminal velocity. Terminal velocity, that means with the subscript. There is constant velocity which it is falling down. So W minus U will keep in one side is equal to F. Put the value W. W value is what? Mg. You can write Mg minus V rho g, and this value is write as 6 pi theta r Vt. Now mass, again we are changing mass equal to volume into density. Volume of this drop into density of this drop. Volume of formula is 4 pi by 3 r cube, and density of the object, spherical object is d into g minus v. Again we can write for this also 4 pi by 3. This v stands for volume of the object which is experiencing an upthrust by the medium. So 4 pi by 3 same value, 4 pi by 3 r cube rho g is equal to 6 pi eta r v t. Terminal velocity. We have take common. 4 pi by 3 r cube is common. Here we have d minus rho into g is equal to 6 pi eta r v t. Let us cancel. Pi and pi cancel. 1 r and r cube it is cancelling. R square is left. 2's are 3's also. You can make Vt the subject of formula. The value of Vt will come 2 upon 3 3's are 9 r square d minus rho g upon eta. This is the formula of expression for terminal velocity. Using this expression we can find the terminal velocity. That means the constant velocity which the spherical body will be falling down in this medium. Constant velocity. It may either fall down, it may even go up, depending upon if the d is bigger than rho, that is d is bigger than the body is falling down. If rho is bigger than d, the body will be going up. If rho is bigger than d, the value of Vt will come with the negative sign. Negative sign means the body is going up. That means the body is rising. With this velocity, only constant velocity, only the body will be rising up. For example, air bubble in water. Air bubble in water rises up. The reason is same only because the density is less, and that this is the velocity with which the air bubble will be rising up. In question, when they say neglect the density of the air, if it is air, then neglect the density of the air, that means rho value will take 0. Rho is the density of this medium in which the spherical object is moving, or in which the spherical object is falling. Rho is the called density of that, and d small d is the density of the spherical object. So this is the expression. So this was the theory portion of this chapter. So next day we will be problems.